start. I didn't give you a quiz last time. We, I guess, about to discuss such functions as secant and cosecant. And well, I guess let's start and recall, for example, the graph of function sine. And related to it, we're going to produce the graph of function 1 over sine, which is cosecant. So function sine goes in between negative and positive 1, and it keeps repeating itself, and it has 2 pi period. In other words, if you know how to graph piece from 0 to 2 pi, then you can graph the rest just repeating this whole thing. For the graph of function cosecant, we utilize the graph of function sine, which is going to be shown here. And actual graph of function sine does not have much to do with cosecant. You can see the cosecant is in blue, and the way it's produced is by taking the points of intersection, since if you think about cosecant of x, which is actually nothing else but 1 divided by sine. So in other words, we have values of sine in denominator, and in denominator we cannot have zeros, and that's why when 0 value appears for sine, where is the 0 value? Well, here's 0 value, here's 0 value. Value means y coordinate of the point. Intersections with our x-axis, in other words. Then we have asymptotes. So the way it looks from the top point on the function sine on the level of 1, we need to hang like a little parabola-like piece, which is not a parabola since it just has vertical asymptote on the top as well as on the bottom. So these two pieces actually going to repeat again and again and so forth, and those two pieces are values of function cosecant. In other words, if you have ability to graph function sine, then automatically you put this asymptotes and hang pieces of graph of a function cosecant on the bottom and on the top, and that's, I guess, the way to graph. So it's just one little extra that I can add about graphing function cosecant as well as function secant. Turns out they go nicely together. So you just need to graph function sine or cosine. So let me do problem 29. It wants us to graph secant. Well, actually, let me do cosecant first since we started. Maybe I'll do 39 first, and then we'll do 29. 39 says y is equal to 2 times cosecant of 1 over 3, right? 1 over 3 times x. Okay, so we just need to take this corresponding function sine, so minus 1. Minus 1 we'll do later. Remember, we'll always leave it for the end. So my goal will be to deal with a graph of function cosecant that corresponds to 2 times sine of 1/3 x. So this will be my goal, my step number 1. And I already know how to graph function sine of x. We just did it. So let me also graph it with red colors. So this is something that goes like that, right? And all I care about is to put this period of actually the amplitude of 2, and then decide on a period. So I'm going to be restricting my argument in between of 0 and 2 pi. I hope you still remember these procedures. So we now need to triple, so we get x isolated in the middle. That way we produce period of functions. So x is in the middle, that's what I need. And x varies from 0 to 6 pi. Okay, great, so I put 6 pi here. It looks like it's a 6 pi, 3 pi, so multiples of 3 pi. Now I'm gonna hang pieces of that function cosecant. I don't need to do this at this stage because I still gonna need to subtract 1, but just to show you where this actual cosecant is hiding. Here on the top and there on the bottom. So we have these pieces and there's more, of course. So this will be graph of 2 times, and we have cosecant of that argument, 1/3 x, whatever it is. So now I need to do that -1 procedure. Subtract 1 to get the actual graph. So this whole picture should go down 1 unit. The whole picture. So let me make it separately. So it's already messed up pretty well, this whole thing. So I'm gonna prepare the asymptotes are here. And then we're gonna need to move down our function sign. And it's not starting at the origin. Since it's moved down, it starts at -1 and it goes up to +1 and then up to -3 level. So somehow I should fit it here, that and there. I guess it's easier to first put function sign and then asymptotes, because otherwise you need to be careful. But anyways, I just moved this whole thing by 1 unit down. So my cosecant that I automatically hang here on the top and on the bottom will be right there. And the whole point is to clearly show the period of 6 pi and also where it's in between of -3 and +1. And that's it. So when you graph the sine function, that's all we need, because after that you just change its period a little bit and change maybe move it up or down. So analogously, I'm gonna do exercise, which one is 29 with a secant. So for exercise 29, I'm gonna prepare a reciprocal of function secant, which is a cosine. So what I'm gonna need is to think of a graph of 4 secants of 1/2 x, and for that matter, the graph of cosine is going to be heavily utilized, the one that starts upwards, sinks down, and returns back. So that's the piece on the interval from 0 to 2 pi for the function cosine, but that's not what I need right now. I need to get the actual period in here. So first of all, I see the amplitude is going to be 4 because we're multiplying by 4. And then I need to put 1/2 x in this bracket in between, as usual, 0 and 2 pi. So whatever the argument is, I just automatically have it in between 0 and 2 pi, just like I did with sine function. So it looks like we just need to double this entire little inequality, and doubling it gives us still 0 on the left side, x is in between, and 4 pi on the right. That's why we did it, because of that 4 pi, because of period. So once I marked that 4 pi, Well, now I'm ready to get the actual secant graph of secant out of my cosine function. So what's the name of this chapter in the textbook? That's the first chapter we learn. It's first section of this whole thing, if you want. So we have, if you're talking about the section, it's 6.5. But so it's graphing secant, cosecant, tangent, and cotangent. But if that's a whole chapter, that's called trigonometry introduction. So whatever question is, but the point of story is we are on page 447. You can always see it here on the right side. Page 447. That's the fastest way to get there. So anyways, let me finish up. Let me hang these pieces of 1 over cosine up here, and then take the lowest you take down here. And that's how it looks like. So just produce the graph. So all that was preparation to get the actual blue little pieces hanging on the top and on the bottom. So basically with graph functions, sine and cosines, we just have one little extra step. You're very welcome. So I'd like to take a look at section 6.6 that actually doesn't bring us with any new information here, just I guess graphs more, just graphs more, and that's dealing with only sine and cosine, because we already know that those are like key functions for graphing. So I'll just graph some more. I guess there'd be nothing else I could add to this story except for just graphing more, and that's it. So that's the last section of chapter 6. I think for us it's time to already be done with it, because I spent, I think, plenty of time for graphing. And here, if you do a couple of problems, that'd be plenty, because there is not really much in the skill building exercises. We have just this little group. So let me try, say, exercise number 9, so we can see a little extra they hang on these functions. So first of all, they want you to graph sine function multiplied by 4, so we already know the amplitude will be 4. And here is pi x minus 2, actually plus 2 in the parentheses. So we already know that plus 5 or minus 5 will be done later. So now I just care about graph of function sine, and what I need is to put this pi x plus 2 in between of 0 and 2 pi as usual. So that's my first step, between 0 and 2 pi. So I will see the graph of function sine, where it starts, where it ends, and also top and the bottom. So it looks like there'll be a couple of steps to perform to isolate x. First of all, I'm going to minus 2 everywhere. So my graph is actually going to start not at 0, but at -2. So there'll be a little bit of a shift here. Okay, so now we're going to need to also clear x in the middle, so that pi is what I have to divide by pi, everything. Here, divide by pi, and there we divide by pi. So we isolated our x, so we can see that x varies in between -pi/2, so that will be our first point on the x-axis. And also 2 minus, actually it's not pi/2, it's 2 over pi. I don't know what kind of dyslexia I got, but it's really something that I flip. So it's 2 over pi. Whatever it is doesn't matter to us. I just need to put these numbers here. And then the pi cancels, so we get a 2 minus 2 over pi. So actual shift happens to be by 2 over pi. Where? Well, looks like we subtract 2 over pi, so we move it to the left by 2 over pi. So our axis, let me put this x-axis like that. And the y-axis somehow is gonna go up somewhere. So we'll have 4 for the amplitude, right? So this whole thing will be in between of negative and positive 4. So you can see the period of this function. Sometimes people say period is equal to 2 because that number 2 is what we actually add to the left end to produce the right end. So the whole thing is with 2, and sometimes people like to use letter T for the period. Maybe you will see it in the textbook if you decide to read it. So if you don't read it, that's fine. I think that's enough that what I give you. But point of story is the period is 2, because looks like there was a shift by pi over 2, and that was attained with that little extra number in the parentheses up there. Okay, so that's pretty much all this section is talking about, because other than that, I have to move this whole picture down by 5 units. And if I do this, the graph will go to the level of -1. If I move this down by 5 and down there by 5 will be like -9, because 4 was minus sign down 5. So let me prepare this whole thing again. So there'll be somewhere here y-axis, x-axis. So the whole picture now is in between of -1 and -9. Right? That's the only thing that remains for us to depict on this picture. So we also have this left end as a 2 over pi. You can divide, and you see this is going to be like 2 over 3. Pi is about 3/14, so like 2/3, a little less than 1. And then on the other side is going to be 2 minus that same 2 over pi. I know it's kind of odd number, but in the exercises they can put whatever they like. So now in between of -1 and -9, so I would say on the level of 5, we have these 2 points left and right, and then I have to squeeze my function sign in between. So somehow we got maybe in my graph. And of course, we repeat a little bit to the left and to the right. That's a way to graph these sines and cosines. Only thing is here is my little bit mess up, so I can try to do it a little bit nicer. Maybe again, up, down. Okay, so now it looks much better. So the graph of this function. So what's the key part? Key part is where it starts, where it ends, that main piece, as well as the amplitude numbers such as -9 and -1 in here.
Professor, sorry, so you have 2 graphs for the same equation?
No, this is a graph.
And the graph on top?
The graph on top was moved 4 units down to
Oh,
produce here because
okay.
of the answer. Oh, it's not 4 units, it's 5 units down. 5 units down. I moved it 5 units down. That's how I got from -4, -9, -4, -5 is -9. So that's where.
And why did you go down 5 units?
Well, because that's what they gave me, -5 here.
Oh, I didn't see the -5 because it wasn't. Okay, okay.
-5. Yeah, I didn't try it. It's too much mess. But here's number 9. That's what we're doing. So I graphed the picture and then I moved it down 5 units because of that -5. So that's why we have only one graph, of course. Previous is a preparational for actual answer. And this again, -5 affected -1 and -9 because we actually changed those amplitude numbers 4 and -4 to this -1 and -9 when we subtracted 5 from them. We'll always do that. That's standard. So worth to think about it. I'm glad you are doing it because I know in my pictures it's not very clear because of mess. I'm trying to do my best, but still need to improve. So when I email you this recording, try to do the same problem again. Try to do same problems and you will be pretty well prepared for everything related to this class. These exercises, yes, they are tedious. This little section is tedious. I plan to do one more exercise here and maybe stop with this graphings. It's a little bit too much, I know. Just keep doing the same thing. Let me try one with a negative in front. Here's the exercise 8. I saw minus multiplied by cosine. So let us graph it. So we go with a cosine function that will be with a negative in front of it. So the shape of it is here. I need to know shapes of graphs of sines and cosines, of course, because otherwise, how can we do that, right? So if you recall the graph of function cosines here. See, it intersects our y-axis at point 1, cosine function. Of course, if amplitude is 1, in this case, it's -2, since it's a -2, negative number multiplied by my cosine. So now we have in between minus and +2 and flipped graph. So 2x and minus pi over 2 is in the parentheses. So we're gonna isolate that in between of 0 and 2 pi as usual. And that's actually going to move my y-axis with respect to this function. So I should be a little bit more careful. So in between of 0 and 2 pi, as usual, is my piece of cosine, which is here hanging, that basic one, right? But now I need to pull out x, and it's definitely going to be something else that x is varying in between. So little by little, we add pi over 2 plus pi over 2 to 0 as well. So our x needs to get out. That's the plan. So just pulled out 2x, so there'll be one more step. So this is pi over 2 on the left side, and pi over 2 and another 2 pi. Well, you could leave it like that. You don't have to mess with this fractions, because I think this way you will better see period when you divide everything by 2, or people recommend to times by 1/2, put 2 in denominator. In other words, then you will clearly see the numbers that are on the left and on the right. So it's pi over 4. And then on the other side, we have pi added with pi over 4. So you see the period now, it's happened to be pi. So from
Professor, did you divide by 2 or multiply by 2?
Well, divide by 2 is the same as multiply by 1/2 because you put 2 in denominator.
Okay, okay, thank
So
you.
I put 2, you want to put like 1/2, that's the same thing. So you could do that if you like to multiply by 1/2, if you like that. But yeah, that's arithmetic part of the procedure. So put 1/2. And that's equivalent divided by 2 if you put 2 in denominator, or if you multiply by 1/2. When you deal with fractions, it's convenient to actually multiply by 1/2 because you clearly see that your denominator is going to be 2 times 2, which is 4. So anyways, the period is pi, and now we start. So that's the key part. We started at pi over 4, so we shifted it by pi over 4 to the right. And we end with a pi plus pi over 4. And that does it. This is my graph. You can put carefully the axis here. Put it in red so it'll be same color. The y-axis somewhere up here. And amplitude, which is 2, will be clearly shown then. And the piece of function cosine in between of this numbers on the left and the right, and if you wish you can get more of it, and it's done. So they're not hard, these exercises, they just follow some specific, the 2 facts. First of all, amplitude, and especially if the number multiplied by it is negative, so you have to flip the graph of function cosine. And did I flip? One is, Alex, you did not flip it. So it looks like what I graphed is actual with a plus sign. Or actually I did, I flipped it, yeah. It's flipped, it starts on the bottom, so it's -2. See, I'm getting tired, I need a break, times cosine. So -2 means it's actually starts from the bottom and goes upwards, this piece. And the other 2 numbers, one on the left, pi over 4, and one on the right, whatever it is, and it's always produced the same way, that pair. You put the argument in between of 0 and 2 pi, and I think that's the probably fastest way to get graphs, because otherwise the way that textbook actually shows is a little bit way too tedious, I think. But you can read and see that in the textbook they have their own approach to graph, and you could follow their way because the answer will be the same. I think this approach is most efficient that I keep showing you in this chapter. And as I said, I think it's enough because it's just overdoing the thing, and all you need is just do same problems again, and I'm sure you will get into the pattern. So I did a couple of exercises today from this section. Those are problems number 9 and number 8 here. So be clear, I'll write it down. Number 8. It's a short section, so doing a couple of problems from it is plenty, I believe. And I don't think I want to give you a quiz on this because it's just a little bit too much, right? And plus, graphing is not going to be possible to put in the chat. So next time when we start next chapter, I think it's already time for us to move on to start next chapter. We'll think of something like quiz, and next chapter is going to deal with inverse functions. Turns out chapter 7 that we're getting into is talking about function inverses. I don't want to do chapter 7 right now. As I said, I'm not giving you a quiz. I just wanted to refresh your memories on what inverses are in general. What's the inverse operation or inverse procedure if you try to perform it? For example, if you open the door, what would be the inverse procedure? Well, probably it's to shut the door, right? So you close the door, open, the inverse is closed. And that's the idea that we have here as well. So we do the opposite, we return back where we started. So whenever you have something like inverse, say inverse function to which you probably saw before, parabola x cube. I hope you saw this in the college algebra class. Then to do the inverse procedure, if you cube something, then you need to undo it. You need to extract the cube root. So if your function f of x is x cubed, then people say the inverse will be a cube root of x. So instead of raising to the power of 3, people extract cube roots, so they return back. For example, if they start with number 2, then they cube it. So function f says cube that 2, which is going to be 8. But if you apply the inverse function, which is a cube root, so if you try to extract cube root from that number 8, then you should get back to where you started, to number 2. And turns out there is a way to produce this inverse function by writing x on the left side and y cube on the other side. So you kind of flip this original equation, put x in the place of y and y in the place of x. In other words, you switch x with y. And from here, you can pull out y, just cube root both sides, and that's how you get the inverse. So that cube root is actually this is -1, that's called inverse function. So that's algebraic method to produce these inverses. And if you didn't see this, that's fine. I guess you're just gonna see the idea. You don't have to learn it because that's college algebra. It's MAC 1105. So what we can do to get the inverse in terms of graph is reflect everything with respect to this so-called bisecting line. So that way, x-axis will reflect to y-axis if you had a mirror along this line, and vice versa, y into x. So this y and x coordinates are going to switch, just like we did when we found the inverse. We flipped x instead of y and y instead of x. And that's what happens when you do this reflection. X goes into y, y into x, and the graph actually also reflects and becomes something like that. And if you recall, this is exactly the graph of a cube root. And I guess that'd be the key feature for us to utilize next time, to realize that if you want to graph the inverse function, all you have to do is just take your function and then get reflection through this bisecting line, y is equal to x. And that's what I actually do here when they graph inverse for cosine. So they produce y is equal to x, and that red, actually it's not red, it's blue. It's a blue piece that will reflect somehow like that. And the actual function then will go along y-axis, not along x-axis. That's the idea of this whole story that I tried to show you. But again, we're gonna discuss that next time, I think. It's enough for you for today. I don't wanna have you feel overwhelmed. So we're gonna be slowly getting used to these ideas. And that's the plan. And for now, I'm